Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day, everyone. Welcome back to SID3019. So today we're going to look at the third option for peptides and protein analysis, okay, which is NMR spectroscopy. Okay, so as of today, we are over here. Okay, we will have one more asynchronous lecture next Monday, before we will have your semester break, and we'll come back on the 24th of May to have a synchronous lecture. All right, so that will be another synchronous lecture, and then two more lectures will be given by invited speakers. All right. So again, I would like to start off with encouraging you guys to actually help me to evaluate this teaching style, which is the pre-recorded, and then put it on Spectrum. And if you watch it from Spectrum, there'll be kind of like live tutorial. Okay, so if you like this teaching style, by all means, do scan the QR code and select intervention B. Okay, even if you don't like it, it's still fine. You can still do the survey to help me and my colleagues to actually understand what are your preferences in terms of the teaching style. All right. So let's just go like very briefly on what we have looked at last week. So as I mentioned, that all the teaching or all the materials that we are using for this section is only based on peptides and protein vaccines. So we are not looking at dsRNA or mRNA vaccines, so to say. Okay, and last week we've looked at on how you can actually analyze the peptide or protein sequence correctly. Okay, and the first option that we've looked at is Edmond degradation, okay, whereby there are three critical steps in the process. So the first one is coupling, the second one is the cleavage, and the third one is converting to PTH. And the figure on the right hand side that was taken from Genosphere Biotech company website is basically summarizing the whole thing. So the first one is the coupling, okay, coupling with PITC, and then you get your cleavage over here, and finally you get the conversion of the AZT or the adenino 5 thiazolinone into a PTH amino acid. And then finally from here you can do HPLC, a simple HPLC trace analysis to identify what is the corresponding amino acid. Okay, and number two, we've looked at the second option, which is HPLC mass spectrometry, or mass spec or tandem mass spectrometry. Okay, so in summary, what you have is following your digestion, so you can run either HPLC MS to look at all the mass fragments that you can get. For example, the one on the bottom left hand side is showing you guys that these are the probable sequences, or well, pretty much if your protein is very long and you digest it, then you get a smaller fragments, and these are all the fragments that you will see if you run a mass spec. So in order for you to be able to identify it more clearly, you can either run a HPLC mass spectrometry, whereby you can separate the fragments based on different retention time before actually each fragment being identified in mass spectrometry. Or alternatively, you can just run tandem mass spectrometry, whereby each mass will be reanalyzed and refragmented so that you can actually identify the corresponding sequence. Okay, and the figure on the right hand side is actually showing you guys an example of how this will look like in real practice. Okay, so you can see up over here is actually the whole run. So you can actually see there are a lot of peaks, even higher peaks and what is being shown at the bottom section over here are just a small bit of the whole run. Okay, and then based on this alone, the mass differences between normally the smaller daughter ion to a secondary daughter ion, you can get you can identify an amino acid. Okay, in this case, for example, the first one is corresponding to glycine. Fortunately, this segment over here has no corresponding mass. Okay, so normally if you see that, it will just ignore it. But as part of the training, what you will do is normally we will look at all possible mass differences. Okay, for example, what I'm drawing here is the mass difference between 650 to 745, which has no corresponding mass to an amino acid. Similarly, if you just look at the 707 daughter ion to 745, you don't get any corresponding mass. So we know that this fragment over here, okay, so this fragment over here are actually or very likely is nothing in this particular sense. But if there are actually a peak behind the 650 that you are actually looking at, there might be something else over there. Okay, so you cannot really exclude out that the mass that you observe are nothing. So it might be something, but when you do your analysis, if the mass difference does not correspond to any amino acid, meaning that you'll just either take it out of the equation, or you can just KIV or keep in view for a different mass analysis. Okay, and then once you do get the first amino acid over here, so what you do is you use the second daughter ion, which is 707, and then you you take a difference between that value and the next highest daughter ion, which in this case is 893, and then the mass difference from there corresponds to a tryptophan, and you just continue and do looking at all the mass differences, and you will be able to manage to identify the next one is serine, and then valine. Okay, so that is option number 2. All right, so option number 3, which is the NMR spectroscopy, that is what we'll be looking at. So let's move on. Okay, so NMR spectroscopy, how do you actually analyze peptides and proteins? Option number 3. Let's do, before that, we will do a little bit of review. And that is pretty much what I'm aiming for just today. Looking at a little bit of NMR, just very, very basic theories. And of course, I'll try and finish this lecture within 40 minutes so that I can add in some questions which related to NMR, just for you guys to do a little bit of revision, okay? Because you will see next week that the protein and peptides NMR are not as what you've learned for a simple organic molecules. Okay, so it's slightly different. The theory is still the same, the aspect is still the same, but how you read the NMR spectrum are different. Okay, so let's do a review. First one is chemical shift. Okay, I'm hoping that everybody knows chemical shift. Chemical shift is basically the peak with regards to 0 ppm. So the peak's position with regards to 0 ppm. And chemical shift are normally influenced by the environment of the proton and the carbon-13. So what do I mean here is that depending on the location, so you can have two protons in the same molecule will have two different chemical shift depending on the environment, meaning that if whether they are de-shielded or shielded, they will have a different chemical shift. Okay. Second one, integration. So what does integration means? Integration corresponds to number of nuclei or proton that give rise to a signal. Okay. In this case, if you look at this structure on the right hand side, integration is the kind of like so to say the peak height of the spectrum. Okay, so if you go and measure the change in height for the first peak at 4 ppm, and then you do measure the second one and then the third one, the length of the peak height will correspond to a proton number. Okay, in this case, it's shown here that the ones at around 4 ppm has a height of about 1.2 centimeters, while the other two has the height of about 1.8 centimeters. So if you consider that the 1.2 centimeters as one proton, then you'll get the other two as 1.5 protons. Okay, so to say, and then because you cannot have a half a proton, therefore the first one is always, well, the correct value for the first one that I should say is 2 hydrogen over this one, and then 3 hydrogen for the other two. And towards the end of the day, if you do a deductible, an addition of those three, you'll get the corresponding correct number of protons, which is 8. Okay, and with regards to integration, you need to recall that carbon-13 has no correlation in the sense that it's not the same as protons. So carbon-13 does not really tell you what is the abundance of the carbon itself. And finally, recall multiplicity, okay, which is the numbering of nuclei adjacent to one another. In this case, if you look at here, it's most likely that is a triplet. Okay, so while at 2 ppm it's just a singlet, and at around 1.3 ppm is another triplet. Okay, so you need to try and recall what or why it becomes a triplet. I'm not going to cover it in this particular lecture. Okay, so this is just a revision. Other than that, you need to remember what is coupling constant, J value. I might use this as part of how you identify peptides and proteins, but for now, I will just put it in all the terminologies that are related. Okay, so what is coupling constant, or J? Okay, J or J value or J coupling constant, there are a lot of variation, but pretty much is J. Okay, so it's a value of interaction between nuclei, right? And the last one is about shielding and deshielding effects, whereby as an example, over down here on the left hand side you have an aliphatic protons. Okay, aliphatic protons, if you don't remember, is something like that. Okay, just a linear chain, while on the right hand side you will have what is shown is more on aromatic protons. The easiest example is the benzene. So when you have an aliphatic protons, the protons are shielded. Okay, so shielded nuclei. So imagine, so imagine that is your proton or your nuclei or nucleus. Okay, so as the electron density goes around the protons, okay, again, you don't imagine it as a single electron moving in a straight pathway. Okay, you need to remember that in one of the principles, the position of electron is well, at least based on our current technology, is very difficult to actually determine the path of an electron. So we normally use Huckel theory, whereby you are looking at the probability of electron position, which is also known as electron cloud. Okay, so imagine that you have a big cloud like that. Okay, therefore the nuclei with respect to the magnetic field of the NMR are shielded. Okay, so because you have electron cloud very dense over left and right hand side of the aliphatic nucleus. Okay, aliphatic protons. However, if you look at the more aromatic structure, whereby you have the electron density going around above and below of the aromatic molecules, So the protons on the or at the side of the molecule, so to say, so the aromatic protons are deshielded nuclei, meaning that it will experience a stronger net magnetic field because the electron density does not affect the magnetic field because it's floating, or the electron cloud density is does not hinder the magnetic field, okay, of the NMR. So in this case, you'll get additional effects of aromatic structure on the protons, while on aliphatic you have the opposite. Therefore, you'll get a higher ppm, or a higher chemical shift, while on the aliphatic protons you'll get a lower chemical shift. Or we do in a ppm value. Okay, so just a very basic review. Additionally, recall that samples are normally prepared in deuterated solvent. Okay, the most common ones that you use is deuterated water, so D2O. Okay, remember the abbreviation is not D2O, okay, because the small d is normally you use when you have a distilled water, so a small d. But for deuterated water, you need to use a big D and then 2 and O. All right, so why deuterated water? So 99% of the protons, okay, if you're considering the singular H, okay, one H protons in solvent are replaced by deuterated hydrogen. So a normal hydrogen being replaced by deuterated hydrogen, and it is shown here as 99%. I did not put it as 100% because when you, if you recall, or if you have not experienced doing NMR spectroscopy, you will always have a solvent peak. You know, if you use a chloroform, deuterated chloroform, CDCl3, for example, in the mass spectrum, sorry, in the NMR spectrum, you will always see the chloroform peak as a solvent. Okay, so 99% of it is deuterated, meaning that the signal will not be observable because the NMR machine has a locking system whereby it use the deuterated signal as kind of like a guide. Okay, TMS and deuterated are normally the guide, while you still have a tiny bit of a normal chloroform at about normally less than 1% if it's a pure solvent. And this is the signal that solvent signal that you will normally see. Okay, so you might think like, why do you need to do that? So there are a few reasons why we normally use deuterated solvent. By no means our current technology, so the advancement of NMR, you can actually run NMR spectroscopy using a normal solvent. Okay, it's just that you need to have an experience because there's a lot of techniques that you need to apply to try and reduce the solvent peak. Otherwise, if the solvent peak is too high, then this is what you will see. Okay, swamping of solvent peaks, meaning that if you are actually using 100% chloroform, a normal chloroform, for example, you might use like about 2 mils of chloroform. Okay, so if you convert that into number of moles, it will be quite high compared to number of samples that you use, which is normally or less than 5 milligrams, or sometimes some people use just 1 milligram. Okay, the ratio between the solvent, so number of moles, okay, it's not just a ratio based on the volume or weight, so you need to look at more on microscopic level, so the molecular level, so to say. Okay, so if you convert both into number of atoms, then you will see that the solvent has a way higher number of molecules compared to the samples. So if that's happened, or if that is actually what you did, then swamping of solvent peaks will be observed, meaning that say for example, if you have your NMR spectrum like this, okay, So you might get one singular bit peak for your chloroform, and then you'll see like a very tiny dots, which are your samples. Okay, so this is what I mean by swamping of solvent peaks. Additionally, if you use a deuterated solvent, you'll be able to stabilize the magnetic field of the NMR. Okay, so what we do is part of the system, part of the NMR running sequence is for the NMR to lock the frequency to the deuterated signals. That's why if you have experience in running NMR, part of the steps before you actually run your sample is to actually tell the system what is the solvent that you use to dissolve the sample. Okay, so if you use deuterated water, then you will need to choose D2O. If you use deuterated chloroform, then CDCl3 it is. If you use deuterated DMSO, then deuterated DMSO is what you need to use. Okay, so this is so that the system can lock on the signal of the deuterated nuclei, and therefore do an algorithmic system to actually exclude out the large signal from the equation. Therefore, you'll get a better representation of your sample that you are running. Okay, so it's basically it's related, but as I said, nowadays the advancement of the NMR spectroscopy, you might not need to use deuterated solvent, as long as you can actually manually lock on the signal of solvent that you are using, therefore kind of like excluding the signal from the whole equation, thus getting a best signal for your sample. Okay, and finally, the reason why you use deuterated solvent is to accurately define what is 0 ppm. Okay, so that is so normally in all NMR solvents, you have a tiny bit of TMS. Okay, if you don't recall what TMS is, I'm sure your organic lecturer have covered what is TMS. Okay, so by looking at the signal of deuterated solvent and TMS, so it's kind of like the system doing some adjustment on itself, so that your data will be representable, and of course what you want is you want something that is reproducible. All right, so you need to have a balancing system. Similarly to for mass spectrometry and all other analytical instrument, there is always an internal guide to make sure that the system is working in a proper manner. All right, so also recall the possible rapid exchange of deuterated solvent and acidic proton in the sample. So for example, if you have two hydroxy propane, okay, propanol, or two propanol, okay. You need to remember that one way is to verify that you have a hydroxyl group is by actually doing an NMR and then using a deuterated solvent. So if you use deuterated solvent, what you'll see in your NMR is that the hydroxyl group being substituted with a deuterated hydrogen. Therefore, if you do run it before and after, the peak, a broad peak for hydroxyl will disappear. Okay, because the hydroxyl is no longer there, or the hydrogen is no longer there, it's being replaced by a deuterated nuclei. All right, so also this is the most critical bit, is to remember what is 2D spectra 1 looks like, and what does it say, what does it tells you with regards to your molecule. Okay, so for example, a 1D spectra. So 1D spectra alone is a plot of frequency or chemical shift versus absorption of energy. Okay, absorption of energy, meaning that on your y-axis you have your intensity, while in 2D NMR, what you have is a two-axis representing only the frequency. So if you recall, you will have two axes, x and y, and both axes are about frequency. okay, or your ppm. So we have something ppm there, and ppm there, and then from there you will get, you know, mirror image dots and so on and so forth. We will look at it in a little bit. Okay, an example. So normally you will have two types of 2D spectra. We do have 3D, but we're not gonna cover 3D over this lecture, okay? Because it will be too complex, even though 3D NMRs will actually help in protein and peptides identification very quickly, but we will not be covering that because I don't think we have time. But anyhow, so you need to remember that they can be a proton-proton 2D spectrum, okay? So you have a proton spectra over there and another proton spectra on the y-axis and the x-axis. For example, TOCSY or homonuclear correlation spectroscopy, whereby you are looking at proton-proton interaction, typically within less than 3 bonds. So if you have again a propanol like this, where you have a methyl methyl group on the both ends of the molecule, okay? So a cozy, what we will see in a cozy is interaction between these two protons and these two groups of protons, okay? So you have the methyl groups and the the protons in the middle, and also you, because 1 2 3 4, normally typically it's 3 bonds length, so anything further than 3 bonds length you will not be able to see it in the cozy spectrum, okay? But sometimes you can actually see, it might be a weak signal, or if you use say a more sensitive NMR spectroscopy, 600 or even 900 megahertz spectroscopy, you might be able to see more than 3 bonds, okay? Additionally, a 2D spectra can be done between protons and carbon 13, okay? For example, the system that I'm listing here is HSQC, or heteronuclear single quantum coherence, and HMBC, heteronuclear multiple bond correlation. So heteronuclear should already tells you that it is actually two different types of nuclear, so heteronuclear instead of homonuclear for cozy, okay? So what are the differences between HSQC and HMBC? HSQC looks at individual carbon-13 signal with their attached protons. So more on looking at a single bond correlation between C and H. In this case, one example of HSQC that we will see is that you will see, if you have a spectrum like that, one is for carbon, okay, ppm, and one is for proton. What you will see is say a signal, a carbon signal like that, and additionally, okay, so you'll get say a proton signal like that, and you'll get a peak or a dot, whatever you want to call it, okay? So then you know that these protons at this particular ppm are actually attached to this carbon 13 at a particular ppm, okay? So it's a very simple technique but useful. HMBC, for on the other hand, is looking at a long range correlation of carbon 13 signal with proton that are normally 2 or 3 bonds away, okay? In this case, this carbon will be coupled to the proton in the middle there, okay, because it's only like 1 2 bond lengths, okay? And you might be able to see 1 2 3, so the hydroxyl proton or nuclei, and you might be able to see the other metal group on the other end, okay? So what I've wrote here is multiple bond correlation, for example, between a single a carbon 13 of interest over there with the proton attached to a carbon adjacent to it, or you can have a carbon 13 and being able to decoupled to a proton 2 carbons away. Okay, so basic concept. But for protein and peptide NMR analysis, of course, we'll typically only using 2D or 3D NMR. We do not use just one NMR, because you need to understand that protein and peptides are very complex. Therefore, you might not be able to clearly identify or clearly look at your spectrum and say, this is the proton. Okay, because imagine if you have an amino acid, so basic structure of an amino acid, and then you have an R group over there, and then you'll have your carboxyl at the C terminal and amine at the N terminal. So that's the basic. You can have different R groups, for example, and just based on one amino acid, yes, you can clearly use one NMR to identify the amino acid. But imagine that once you have this multiplied by I don't know, let's say just a normal peptide, 20 amino acid, now your NMR spectrum will be more complex and there will be a lot of overlappings. Therefore, you normally use a 2D NMR or 3D NMR to actually identify the sequence individually. Okay, we will look on that next week. All right. So the common 2D NMRs that we use to identify a protein or peptide sequence, one TOCSY, okay, again proton-proton interaction. You can use NOESY, nuclear Overhauser effect spectroscopy. We will look at that in the next few slides, and also TOCSY, which is total correlation spectroscopy. So the first two are looking at a homonuclear interaction, while the third one, TOCSY, is looking at the heteronuclei interaction. Okay, two-dimensional spectra in which cross-peak identifies protons which are coupled, usually vicinal or geminal related, but also long-range interaction may be seen. So the keywords over here is cross-peak identification. We will look at it in the next slide. And also just the terminology, vicinal and geminal. So vicinal is two protons connected or adjacent to one another, okay, but it's interconnected between another carbon, so it's not in the same carbon. Geminal is more on the same carbon. So one way to remember it is geminal, if you watch a lot of movies, Gemini, for example, whereby Will Smith are actually one of the actor. So remember that in that movie, the movie is about twins, or well, the movie is not about twins, so to say. It's about cloning, but you can consider that as a twin. So geminal is twins. So what you can see here is that you have a single parent, one carbon, connected to two hydrogens. So the two hydrogens are twins. Therefore, you call it as Gemini. Vicini, you just remember, if Gemini is twins, then Vicina is the other one. All right. So that's just how at least I remember it. Now, what is COSY? We will look at COSY in just one slide. COSY spectrum signals on the diagonal line are an indication of a chemical shift values of each of the proton signals. Okay, so a proton-proton that are coupled or linked to each other within less than 3 bonds. So in this case, for example, we have two nitropropane. Okay, so propane is like that, and you have two nitropropane. So you have sorry about the notification. You have a proton over there, and then you have 3 protons on either side of the molecule. Okay, so if you do a 2D COSY spectra, whereby you just take the proton spectra and then you put it on x-axis and put it on the y-axis, what you will see is you will see an interaction peaks. Okay, in this case, for example, so these are the peak of interest. Okay, so you have one over there, and highlighted in red dots, and then another one highlighted in blue dots. So which one is blue, which one is red? If you have a guess, that one should be the red ones, okay, because the chemical shift are not on the downfield, and you will have that one, it's more on downfield, which is in blue. Okay, so what you will see is, if you looked at the X and Y, you will get like a huge peak forming when these two protons are proximate to one another. And additionally, you'll get to see that this proton and that proton, okay, because it's 2D NMR, you will see another peak on that particular region. Okay, so I wonder how long is the lecture already. Okay, so by doing this, when you draw a diagonal line, okay, in the middle there, that is kind of like the mirror image for the whole system. Okay, so anything that has a correlation, you will see another peak forming. Okay, for example, like that one. So you know that this one correspond to the methyl group, okay, and that one correspond to the you can call it alpha hydrogen. Okay, so you can see that there are peak forming between those two. So you know that this methyl are actually connected to the alpha hydrogen. Okay, so by doing this, the peak over there shows that the methyl are directly connected to the other protons. Okay, a vicinal proton, not geminal. So this is geminal. Okay, that one is also geminal. But when you have a peak like this, so you know that it is vicinal protons. Okay, so that's why the terminology is important. So by doing this, you can accurately say that this is the correct structure. Okay, all right. So that's it about COSY. When we look at NOSY now, it's more it is still a proton-proton signaling. Okay, but this time around, instead of through the bonds, so NOSY is a signal through space interaction between the molecule. For example, this is just a simple example that is shown here. So over here, the peak of interest that that I'm trying to get you guys to see is these two protons over here. So you have a proton labeled H5 and a proton labeled H2. So the question now is, what is the stereochemical configuration of H2? Okay, so by simply using a NOSY, you can't really see, well, we can't really tell whether that protons has, say, for example, L or D configuration. Okay, just an example. Because COSY move through bonds. However, NOSY move through space. So the interaction moves into space. So if you count the bond numbers over here, you have 1, 2, 3, 4. So it's 4 bonds. Yes, you might be able to see it in COSY, but you'll be able to see it clearly in a NOSY 2D NMR system. And how do you actually do that? Well, as what we did in the previous slide, the first one is to actually draw a diagonal line. Okay, so diagonal line is to show that this is, if you flatten out the diagonal line, you will get to see the same spectrum again. Okay, so this is a 2D line, a diagonal line, so it's kind of like a 2D contour, so to say. Okay, and by looking at this, what you can see is that you'll see that this peak, which is corresponding to H5, okay, actually has an interaction with that signal over there, and then this signal. Okay, and you know that this one is H2, that one is H5. And from the diagonal line, if you move from one of the peak into the overlapping peak, and then moving to the next one, you can actually tell that those two are close in proximity using nosy. Okay, so if you know that they are close proximity, if you imagine in the 3D structure, okay, over here is a dash line, okay, and this one is shown as a zigzag line like that, meaning that it can be either a dash or bold. So the question goes back into what are the stereochemical configuration of this particular bond over here. Okay, is it a single line, is it a bold line, or is it a dash line? So because from the nosy signal you can see that this one is H5, you can actually see that H5 and H2 has a nosy signal, meaning that they are close in proximity. So if you look at, if you observe from this side, for example, whereby you have your NH over there, okay, and then of course it's going at the back, like that, ching, ching. Okay, you have your carbon over there. So imagine that this is now a piece of paper that you turn sideways. So because this one has a dotted line which is going down, and then you have the benzyl group going up, and because the signal has an interaction, then H5 over here should also be a dash line, because now they are closer in space, thus you can actually see the signal in nosy. If H5 is actually a bold line, which is, it will be up here, so the signal is further away, therefore you won't see any coupling. Protonic couple. Sorry. Okay, I hope that you'll be able to understand nosy system by just this simple one slide lecture. And additionally, for TOCSY, it's similar to COSY, proton-proton neighboring coupling, inclusive of the entire spin system. Okay, so it's similar to COSY, but it's not identical, meaning that it's inclusive of the entire spin system. You will see all other protons. So in other words, this proton, or Hi, is connected to that proton, Hi plus 1, is connected to the other proton in Hi plus 2. So you will see, in this case, for example, this proton over here, okay, so imagine if that is protons, okay, just for simplicity's sake, I'll just draw one proton per carbon, okay. So if you're looking at this proton, you can actually see it is coupled to that proton, okay. Additionally, you can see that this second proton is coupled to that proton, okay, but you will not see this proton and that proton, okay. So this does not happen because now the connection is broken via the ether linkage, so the oxygen in the middle. However, this proton over here can actually see the second proton, okay. See, so this is TOCSY. So the 1D proton NMR spectra is not complicated enough to actually it's not complicated enough, whereby if you just looking at the one sorry, you can see from the proton NMR, 1D proton NMR, you can actually tell that based on educated guess, then these two are in close proximity and those two are in close proximity. Okay, it's easy enough to do an educated guess, but can you exactly pinpoint whether this one is this and that one is that? So this is when TOCSY comes in. Okay, so similar structure, the 1D NMR, make it into a 2D NMR. So this is what you will see. Okay, so you will, as usual, do a diagonal line, and this diagonal line corresponds to, so you know that because the diagonal line shows 1, 2, 3, 4, and 5 peaks, then you know there are 5 different proton groups. Okay, so instead of having one single peak like that, which normally you just say multiplets, okay, now you know that that is actually a two different proton group signals that are overlapping with one another. Okay, so this is one advantage of TOCSY. And what you do next is, as what I've shown previously, is that you go through from the diagonal line. So you see the first peak. Okay, so you know that this proton over here is next to this proton over here. Okay, additionally, when you move in, then you will see that this proton is linked to this proton. Okay, and now you, instead of originally saying that, oh, this one is all the low ppm at the low shift, and this one is at the high. Okay, because that's what I said initially, which is wrong. But using TOCSY, you can actually tell that these two are actually at the low and one at the end, while the other two close to the ether group has the higher shift or low shift. Okay, this one is low ppm, not to confuse you guys. Okay, so low ppm, high ppm. High ppm, okay, so and you can actually see from the TOCSY spectrum that you have another one over here. Okay, and these two peaks, okay, these two are not connected to the other three. Okay, so you know that something is splitting them. Therefore, that is how you actually identify or draw the structure. So you know 1, 2, 3. So this one is the first three, and then that one is the other two. Okay, so that is the basic. Now, this is a bit more complex. Try your understanding based on TOCSY. So draw the chemical structure. I'll give you a hint over here that the structure, the chemical formula is C8H16O, and it has a carbonyl group. Okay, so instead of ether, it has a carbonyl group. So try and draw the structure, and I will give out the answer in the next lecture. And finally, just look at very briefly on protein and peptide and mass spectroscopy. So protein and peptides make structure identification more complex, as I mentioned. Each amino acid has its own multiple atoms and functional groups. So just by looking at functional groups, you have carboxyl, you have amide, you have amine, you have hydroxyl, you have thiol group, you have aromatic group. So these are the basic ones are those three, okay, N-terminal and C-terminal, and these are from the R groups. Okay, so because of the complexity, solvent choice is critical to observe your signal of interest. Okay, so for example, a proton and deuterated hydrogen exchange from amide functional groups are rapidly occurring. Okay, so because it's rapidly occurring and you want to actually see the NH bond. So why do you want to see that? Because amide bond is the basic backbone of is the basic backbone for peptides. Therefore, as best as you can, you want to actually see all this NH coupling, and because you do have a different nosy and TOCSY, for example, you can actually identify one amino acid to another amino acid. Okay, so you want to see the signal. Therefore, what you normally do is, instead of using 100% deuterated solvent, this is one critical differences between a normal NMR that you run for a normal spectroscopy and peptide and protein NMR spectroscopy. You normally do a mix of about 10% of distilled water and deuterated solvent. Okay, so this is to reduce the exchange, and therefore you will still be able to see the NH signal. Okay. Additionally, what you can do is you can actually control the pH of the reaction mix. Now, because you have water in there, so you can have well, even deuterated solvent is technically heavy water, so you can still see effect of pH and temperature in your NMR spectroscopy. So what you can do, the second one is you can control the pH to reduce the acid proton exchange with the solvent. Um, and as a guide, the backbone proton and H exchanges slowest at pH 3. Okay, so the lower the pH, the slower the exchange. It's basic concept if you have an amine group. So if you go into a lower pH instead of the what you will see is actually an addition of protons. So it's a similar concept. So at lower pH, then you will see the proton is still intact to the amine group or the amide group, so to say. Um, okay, so but if you go too low, um, hydrolysis of amide bond can occur. Okay, so if you go very low, for example 0 or 1, then instead of stopping the proton exchange, you will actually hydrolyze the amide bond. Okay, so pH of choice are typically between the 4 to 6 for your run. So this is an example of intrinsic exchange rate of a proton and a heavy proton versus pH in aqueous solution at 25 degrees Celsius. So what I said just now is this one. Okay, so the NH exchange, and you can see as a change of pH. So that is the lower you go, the exchange is slower. Oh well, in this case it increases again because of hydrolysis of protein. So the optimal is around 3, but still it's still low that it will hydrolyze your peptide. So you can go higher up until about that range. Okay, so that is the normal range that we use. Okay, so I think that's all for today. I'm actually at home because I have to quarantine myself. I'm waiting for it's very unfortunate. My son's classmate was diagnosed with COVID-19, so I'm currently just staying at home waiting for the results. And if everything is fine, then I will be back at my office, and I will, if you notice, there's no picture of me in this lecture because I don't have a camera at home to actually do this recording. All right, so that is all for today. And these are some references that I've used. And of course, I'll be really grateful if you guys can actually spend some time to do the survey. Okay, so you can just QR code this one. And other references, including my PhD thesis on peptides and some other internet resources. I'm sure you guys have used this chemistry LibreText, so it's a very good resources. Okay, so you can also look at a book by University of Zurich in Switzerland, so which talk about peptides and proteins, NMR, by this professor Zebra and Beder. Okay, so you can just quickly just go to this link. It's a very long link, so I'll just make it short: gg.gg /UGGOJ. Okay, and also the lecture was created using internet lecture notes from University of Queensland, Australia. That's all for me. Thank you, and I'll see you guys in another recording next week. Okay.